Okay. Good afternoon, everyone. My name is Tianmi in Electrical and Engineering and Computer Science. It's my great honor and pleasure to introduce our next speaker, Professor Pallab Bhattacharya. The title of the talk is Off the Beaten Track from Glacier Way to Quantum Dot Lasers. So Professor Bhattacharya is a Charles M. West Distinguished University Professor and the James R. Mellor Professor of Engineering in the Department of Electrical Engineering and Computer Science at the University of Michigan. Professor Bhattacharya has authored the textbook Semiconductor Optoelectronic Devices. Now it's in its second edition. Professor Bhattacharya is a member of the U.S. National Academy of Engineering. He has received numerous professional awards. I will only list a few here to save time, including the John Simon Guggenheim Fellowship, the Heinrich Welker Medal, the IEEE David Sarnoff Award, the Optical Society of America Nick Holoyak Award, and the TMS John Bardeen Award. He's a fellow of the IEEE, the American Physical Society, the Institute of Physics in UK, the Optical Society of America, and the National Academy of Inventors. Professor Bhattacharya is credited with the demonstration of the first room temperature quantum dot lasers. Let's welcome Professor Bhattacharya.
Thank you, Zarian, and good afternoon, everybody. Well, Steve, that's a hard act to follow. So let's see. Now, this title is it's serious. You'll see the relevance in a minute. So this talk is about lasers, and lasers are everywhere. In fact, lasers and transistors, these are the two devices that we live with, that makes us live our lives. And these are some of the applications. There may be more of infrared, near-infrared lasers, and now with the visible lasers, there's a whole bunch of other applications emerging, like displays and projectors, and plastic fiber communication is becoming important, and of course, optical storage and so on. So lasers as we know them, well, Einstein wrote the rate equations more than 100 years ago, or just about that time. And the three dominant processes in a semiconductor are spontaneous emission, stimulated emission, and what I call stimulated absorption. And these are some of the rate equations, the Einstein coefficients, and most importantly, the Bose-Einstein distribution, or the photon number, which really governs how lasers work. And first came the atomic lasers, the multi-level, multi-state atomic lasers, and you can see what happens there. Everything is good about these, except you cannot excite them or pump them electrically. And they are, of course, very bulky. Then came the semiconductor lasers. Here, instead of discrete states, you have bands of energy, and these provide both advantages and disadvantages. The first thing is, with semiconductors, you can dope them P and N type, and therefore you can make electrically pumped devices. However, because of energy bands, the carriers spread out in energy, and this leads to high injection to gain compression. And therefore, they become very temperature dependent. The thresholds become extremely temperature dependent, and this is a real problem in real applications. And of course, the line widths, therefore, tend to be a little broad also. This gain formula for lasing in semiconductors, I'll come back to this in a minute. So that's the basic mechanism. Electrons and holes recombine and give you photons by stimulated emission. Now, so this talk is about quantum dot lasers. So what are quantum dots? So in terms of quantum confinement, first came the bulk material. And so all the dimensions in all directions are large. Now, if you confine them in one dimension, in one direction, then you get what is called a quantum well. And in that direction, the size is of the order of the carrier wavelengths, the de Broglie wavelengths. If you confine them in two directions, then you get what we call a quantum wire. And if you confine them in all three directions, you get a quantum box or a quantum dot. And just to put things in perspective, you have to line up about 10,000 of these quantum dots to match the size, the diameter of the human hair. So that's how small things are. That's what. So we had started doing these things long before this word nano was discovered. So going back to a semiconductor laser, there are essentially two kinds: an edge-emitting Fabry-Perot laser, or you can have a surface-emitting laser. And in the active region, the gain region, as we call it, you can have bulk material or quantum wells, as we have shown here, and so on. And now going back to that gain formula for a minute, the two most important, or the three most important elements here is this difference between the Fermi functions, which is the equivalent of population inversion in a atomic laser, the joint density of states, which has to be very large for large gain, and also the overlap, the momentum matrix element, which comes from the overlap of carriers. So we have to play with these things, maximize these three terms to get maximum gain. So with large density of states, you get high gain, high differential gain. And this with what we need also is a discrete energy spectrum, just like the atomic laser, so that we can have high temperature stability. So as you pump the laser, the carriers have nowhere to go. They are stuck in the discrete states, and so that gives you that thermal stability. The large differential gain gives you a whole slew of things: low threshold current density, large output powers, potential for high-speed operations, small line width enhancement factor, and dynamic chirp. These are very high-performance factors. This is what you're looking for in the lasers that go into transatlantic communication, transpacific, and long-distance communication, and so on. And the spatial localization of electrons and holes that you can get in a quantum dot, that in addition to providing high joint density of states and an overlap integral, it also localizes the carriers and kind of shields them from defects, therefore gives them radiation tolerance, and so on. So those are the advantages of a quantum dot laser. Now, in 1982, Yasu Arakawa and his mentor Hiro Sakaki, they did a very clever measurement, and they reported this measurement. First, they calculated theoretically what the temperature dependence of a threshold current would be for a normal bulk, or as we call a three-dimensional gain media laser, for a quantum well laser and a quantum wire laser and a quantum box laser. So you see these four in the bulk laser. The threshold current goes all over the place with temperature, and that's not good. And in a quantum dot laser, you can see there is no temperature dependence. The characteristic temperature, as we call it, is infinity. And this happens, again, because there are discrete states. The carriers don't thermalize, as in a bulk material. And then, to demonstrate it experimentally, of course, in those days, nobody knew how to get a quantum dot or a quantum box experimentally. So what they did, they applied a very high magnetic field in the z direction and used a high mobility material for the gain region of a bulk laser. So they actually had a double heterostructure laser, and they applied a high magnetic field so that the carriers actually under this magnetic field actually completed a cyclotron orbit. And in that state, the carrier motion in the transverse x and y directions are quantized, and they form discrete Landau levels. And in that, with the application of a high magnetic field, they could demonstrate that, yes, indeed, in a simulated quantum wire laser, this one, indeed, you can have good temperature stability as predicted theoretically. And this was a landmark experiment and a paper. This showed that, yes, if one uses lower dimensional quantum confined structures in a laser, one can derive a lot of these benefits, not just temperature stability, but all the others that I had stated. The problem was, how do we, and well, before I go to that, so what kind of quantum dot do we need? So this is the shopping list. The size should not be too small. They should not be too large for these reasons I've listed. For large modal gain, you need a large density of these dots. They should be uniform, low concentration of defects, anything that you can wish for. Of course, we didn't have a clue those days how you would get these. So we knew that it demanded, it would place huge demands on the fabrication technology. So the simple-minded way to get a quantum dot, and I'm talking about the very early 90s to mid-90s, was to grow epitaxially a quantum well structure, as you see that, and if you can etch it down through a mask, and you can then possibly get an array of such quantum dots. Now, in those days, in our facility down the road, we had an E-beam system, but it wasn't as good. So I sent my student then and my colleague now, Jamie Phillips, to Clivia Sotomayor Torres in Glasgow. She's now moved to Germany. She had the best electron beam facility in the world at that time. So I sent Jamie there, and he came back with these beautiful arrays of quantum dots. And well, we did all kinds of experiments, spectroscopic experiments and characterization of the luminescence, time resolved, and all kinds. And you know, you get good papers out of these. But that's about it. I realized you could never make a laser out of this because, as you see, a laser heterostructure is pretty complicated. And you have to grow multiple layers. You have to grow layers below this, layers above that. There was no way you could do all that with this. So it was clear that with this kind of technology, you just couldn't have a practical device. Others still kept on trying, but I was convinced it couldn't be done. Now, Jamie, of course, did all this nice work, but he also came back with a very deep appreciation for Scottish beer. And so we killed two birds with one stone there. When I came to Michigan in the very early 80s, I was convinced that the way to go was to use trained layers, both with gallium arsenide-based systems and with indium phosphide systems, and the latter was more novel. And I struck a collaboration, one of the most fruitful collaborations I had, and there were many others, as you'll see. In fact, this talk is all about collaborations, with Ron Gibala, and we shared a very smart student, Kevin Chang. I mean, they're all smart. But this is some of his work out from textbooks. He was looking at the formation of dislocations and the critical thickness of strained pseudomorphic layers and strained layers. And this is, you can see, the misfit dislocation network. This is all his work. Of course, with me, he also made transistors out of these heterostructures and so on. So that was what got me started with strained semiconductors. And then with these strained semiconductors, we were making, we had a very large program, actually the first batch of URIs those days. One of the first ones came to Michigan. George Haddad was the PI. And under that, we had chartered to do all kinds of things. And one of them was to develop the highest frequency transistors that we possibly could, obviously submicron gate and all that. And so we started working on submicron modulation-doped FETs. And what you have here is a modulation-doped high bandgap, low bandgap heterostructure. And the electrons then transfer to the low bandgap material, and that forms the high mobility channel. And actually, the inventor of this device, Mimura-san, he got the Kyoto Prize for this year. So we started with indium phosphide-based heterostructures, and what we started doing was in the channel started adding more and more indium to lower the band gap, increase the mobility, and also that increased the band offset and therefore the transfer doping efficiency. And so these are some of the results, and we started adding more and more indium. So 53% is the lattice matched composition, and then we started adding 60, 70, 80%, and as much as we could. And these are some of the results of the mobility of these heterostructures at room temperature and low temperature, and then the actual, in the submicron devices, the measured cutoff frequencies and the transconductance or the gain. And you can see we were making pretty decent devices, very decent devices of transconductance over 1,000 millisiemens per millimeter and cutoff frequencies of about 200 gigahertz. This was state of the art at that time. But one thing you notice, and we noticed at that time, that all these parameters were increasing, they peaked, and then they would go down. And we just didn't understand this. Now, about the same time, I live close by off a road called Glacier Way. Many of you know that. And it used to be, when we moved there, it used to be a dirt road, which was a royal nuisance. Gil Oman actually coined the term that our children, when we actually started fighting with the city and others and so on, said our children were van-trapped because they just couldn't go anywhere. They couldn't even walk to school. So anyway, so we had a committee and all that, and my job was to take pictures of this road, different times of the day, and look at how bad or good it got. And every morning I would go for a period and I would see these cars bouncing around. There were hubcaps lined all over the place. And so that was that. And I realized two things. One was, and I used to observe the wheels as they turned and lost their hubcaps. So when the diameter of the wheel matched the roughness scale, they would be bouncing the most. On the other hand, if the wheel was very large, or if the roughness scale was very large, relatively, then it didn't matter too much. Things were fine. So that was that. And that reminded me of an experiment one of my students had done a few years before that. And we were looking at a phenomenon called scattering mechanism called interface roughness scattering in interfaces between two semiconductors and how they affected the luminescence of quantum wells or the performance of transistors and so on. And you can see as the roughness scale comes close to the electron wavelength, the mobility goes through a minimum. The scattering rate goes through a maximum, and therefore the mobility goes through a minimum. And I asked this student, by the way, this student is now one of the presidents of Samsung. I asked him that, can you model that peaking of the mobility that you saw and model it this way and see what kind of roughness scales you get? And he came back after a couple of days and he said, yeah, I can fit that data, but you won't like the kind of roughness. It's absurd. It's nothing like a height of 2.8 angstroms and a lateral extent of a few angstroms. The height I get is much higher and so on. And I thought there was some mistake in the calculation, and I kind of forgot about it. But what we were really seeing, what his calculations were exactly right, and what it predicted was we were forming quantum dots at that interface, self-organized quantum dots, and which really looked something like this. So this is how we in Michigan actually accidentally hit upon, while there were other groups around the world, they were tweaking their growth conditions to get these self-organized things. We kind of hit upon it in a very accidental way through these transistor results. So then, of course, once we knew what might be happening, then we did some careful experiments. And one of the pioneering experiments that was done was, I remember Paul Berger and we on a Friday afternoon, Friday evening actually, he took my video camera, and of course in the process he destroyed it also, but he measured these integral scale read spacings. This is glancing high energy electron diffraction that you can do in situ in a read thing. And there were several things we observed. One was, so we started growing indium gallium arsenide with different compositions on gallium arsenide, and we saw that the moment we open the indium shutter, after a few oscillations, the read oscillations die. And this was not as one or two authors had previously predicted, this was not the critical thickness. All this was happening way before the critical thickness. And we knew this had to do with the three-dimensional growth modes in the pseudomorphic regime. And we predicted that in the pseudomorphic regime, the surface lattice constant will, instead of a step jump at the critical thickness, it will approach the critical thickness in a monotonic manner. And that's what we saw from these the read data. And of course, as you lower the temperature, things the kinetics is not there, and it cannot reach the critical thickness. So we realized that under these conditions, you have a three-dimensional growth mode even before the critical thickness is approached. And this is an equilibrium phenomena, but it is the formation of these dots are kinetically driven. In fact, my colleague Jaspreet Singh, based on energy minimization on the growth surface, he came up with this very simple formula that the n cube, this is the number of monolayers, the height of these dots is dependent on the ratio of these nearest neighbor, second neighbor, bond energies, and the critical thickness, and the substrate lattice constant. And with that, we predicted that for a mismatch greater than 1.8%, and it's now known as the 1.8% or 2% rule, you will have the formation of islands. And we were glad to see after many, many years when people started working on nitride semiconductors, that 2% rule was borne out here also. When you grow indium gallium nitride on gallium nitride for 18% indium or higher, you get this 2D to 3D growth transition. So this put the whole business of quantum dot growth on a mathematic, at least we understood it quantitatively also, and we knew how to grow and design these things. About that time, Brad Orr in physics, he had just joined the physics department, and he spent some time building an in situ STM, and he got these first STM pictures of these quantum dots as they were growing. And here is some of Rachel's work. She did the first cross-sectional STM, and on some multi-dot layers we had grown. And here you can see these multi-dot layers. Here is some more data. So we gradually realized what their shapes and sizes were. They're kind of pyramidal in shape. And here's some very important work. This settled it once and for all, that yes, you do have a wetting layer. It's a Stransky-Krasnov growth mode, and the quantum dot is kind of immersed in that wetting layer. And this had tremendous ramifications in understanding the carrier dynamics and all kinds of things going on, as I'll come to later. And here's the photoluminescence of these dots, very narrow line widths in spite of the size distribution and all that. And here's the luminescence from the wetting layer. So now that we knew what we were doing, we ventured to actually grow a laser heterostructure. And we made the first, the laser that actually worked at room temperature. And we sent it for publication the moment we got the results. And Ted Norris did some of the time resolved measurements, which are not shown here. We sent it off, and we sent it to electronics letters. Now, electronics letters has an impact factor of, currently it's less than 1. And, but we sent it there because I knew there were probably other groups working, and I knew that this paper would be out in less than 5 weeks, 4 to 5 weeks. And indeed it was, and thank God we sent it there, because within a month there were 2 more papers with similar results. So that was that. So that was the first room temperature quantum dot laser, lasing at about 1 micron, as you can see. My group focused on the dynamic characteristics because I knew we could learn a lot, and I was working on high-speed quantum well lasers at that time. So I knew we could learn a lot about the carrier capture and emission processes and all kinds of things, efficiency and all that from the dynamic measurements. And we noticed something very regular right off the bat. As opposed to any other kind of laser where the modulation bandwidth, this is a small signal modulation response of these quantum dot lasers, as opposed to any other laser where the modulation response does not depend too much on temperature, here it was very much dependent on temperatures. As we went from cryogenic temperatures to low temperatures, the modulation bandwidth increased a lot. And we didn't understand it at first. Now, the modulation bandwidth of a laser is limited usually by damping. But it could be limited by capture time, and I thought, well, if it is limited by capture time, then we can do an experiment that electrical engineers do. And that is to measure the high-frequency impedance of a diode. And we measured that, and we analyzed the impedance data, as you see, with the rate equations. And out of all this comes out this quantum capture time. It gives you an idea of how long it takes the injected carriers, electrons and holes, to get to the gain region. And lo and behold, as opposed to numbers that are like 1 to 5 picoseconds in quantum well or any other laser, we were getting much, much larger times in these lasers. And this convinced me that this was the modulation bandwidth, the modulation response, the high-speed performance of these lasers were capture time limited, and this capture was coming from some bottleneck. And so I went to Ted. He was the expert on optical, pump probe, femtosecond and picosecond spectroscopy. And so that launched a very, very fruitful, more than a decade-long partnership and out came some beautiful work. And so here are these 2 pulse and 3 pulse pump probe measurements that he did on our lasers, and he unraveled a lot of things. So so you pump the laser resonantly or non-resonantly or just heterostructures, and you observe the population and depopulation of various levels, and here are the transients. But he observed that under certain conditions, the excited state population showed something like this. And this was a signal predicting a phonon bottleneck problem. Now, the N1 to N2 separation in these quantum dots can be larger than the optical phonon energy. And if that is the case, then, of course, you don't have, the carriers just can't come down unless there is some other mechanism. So he sorted all that out, and he figured out that the fast transient is due to what he called geminate capture, when the electron and hole are in the same dot, and the slow transient is due to non-geminate capture, when the electron and hole are in different dots, or the holes are not there. And that's what that is about. And the fast transition from the excited state to the ground state happens in quantum dots, not by phonon scattering or anything, but by a OJ-like mechanism, but it's a 2-carrier mechanism, which we called electron-hole scattering. And this was something very fundamental, that in quantum dots, the main scattering mechanism that relaxes energetic or hot carriers is this electron hole mechanism. And hot electron scatters with a cold ground state hole, gives its energy to the hole, and the hole, of course, comes higher in energy, and then it relaxes by multiphonon emission. And that's how the electron quickly comes down. But as you raise the temperature, the holes thermalize, and there are not enough cold holes for the hot electrons to scatter with, and the process slows down, and that's what slows down the laser modulation and everything else. So we started understanding all our results. The other monumental result that came out of his lab was this direct measurement of the gain recovery of a quantum dot laser. And of course, we saw that by this electron hole scattering, the gain recovery is very, very fast. And you will see that this result, which was again repeated in Japan, by this time we had found out that I had two other competitors around the world. One was Yasu Arakawa, and the other one was Dieter Bimber's group in Berlin. And so this result, you'll see the relevance of this result later on. The best quantum dot lasers that have been produced and which are now, they are universal. All 1.3 micron quantum dot lasers are quantum dot lasers. And this work was done by Zetian himself and a couple of other students. And you see these very, very complicated quantum dot structures where we don't inject from the top anymore. We inject by tunneling, and this tunnel injection laser is also a Michigan product, and get tremendous performance, very high powers, output powers, low threshold. But what got these lasers into the market was the extreme temperature stability. So just like the atomic lasers, now for the first time, you start seeing a absolute temperature stability of the threshold current. And this is just like an atomic laser. Line width enhancement factor and chirp, these are two properties that indirectly tell you that your differential gain is very high. See, when you're injecting carriers, you're modulating the refractive index of the gain region. And this gives rise to chirp. So the lasing wavelength keeps dancing around, and the line width also broadens. And this was measurements actually made on our lasers by S.L. Chuang's. He has passed away, by his group at Urbana-Champaign. And they said, my God, he called me one day very excited. He said, your lasers have almost zero line width enhancement factors. And I said, well, that's what's theoretically expected. And then I'll just repeat one more thing. These are 1.55 micron lasers. Now, when you grow quantum dots, so you try to grow quantum dots on indium phosphide-based heterostructures as opposed to gallium arsenide, you can't grow quantum dots. They tend to, from the kinetics on the different directions, they tend to grow as what we call quantum dashes, little segments of islands. And it took my students a while to actually figure out the conditions of how to grow real quantum dots. But once we got them, of course, and then these results were repeated in Germany, and they're still being worked on. And we got, again, beautiful results, very low alpha factors and chirp, and again, extreme temperature stability. I might add that the commercial 1.55 micron lasers made out of indium gallium arsenide phosphide quantum wells have T0 values of about 40 Kelvin. So this is what has now put these lasers in the market, and there's one company, Ranovus in Germany, that's marketing now all the 1.55 micron quantum dot lasers. I'll skip these. The quantum dot lasers, you may think that these are tiny things, and so they can't give enough power. But here's this is not our result, but just to show that this laser is giving out about 7 or 8 watts of power. And this laser, which you cannot see with the naked eye, this is what, to get this kind of powers, you'll need something like that. And of course, you need power for all kinds of applications. Here's one back in the 80s. Now, of course, Goldfinger could use a quantum dot laser to do that. So let me shift gear. One emerging field which has become very important is silicon photonics. Everybody is convinced that there has to be some amount of optical communication on the chip or between chips and so on. We still don't know what the exact form of it and how much of it will be there, but there is no doubt that it's going to be there. And for this, the holy grail is that you need an electrically pumped, compact semiconductor laser, preferably monolithic and not bonded and so on. So years ago, we said, let's grow them on silicon. Let's see what happens. So we did that. So the first laser was made by another student, Kojo Linder. He demonstrated lasing of a gallium arsenide quantum dot laser on silicon working at 77K, and then Zetian demonstrated these beautiful results of room temperature lasers, and now they are being made by IQE and others for commercial applications. So there is a company in China, Huawei, that's producing them mass scale. So these are now, again, something that's one option for lasers for silicon photonics. And we did another thing. We used these quantum dots in the buffer layer itself. These quantum dots act as filters for this to trap dislocations, and they work very effectively as dislocation filters. So we used quantum dots not just in the gain region, but also in the buffer region. So these, I mentioned that very fast, ultra-fast gain recovery, and that property came in very handy for these wideband polarization insensitive amplifiers, semiconductor optical amplifiers that was demonstrated in Japan. They're being marketed by QD lasers in Japan. And they can work at very high power levels with zero power penalty and at very high bit rates and so on. So again, these are very wideband optical amplifiers that are competing with fiber amplifiers. Okay, another few minutes, another arena. Now, fast forward several years, we had started working with nitride semiconductors. And of course, when you think of nitrides, you think of all these different kinds of applications: mobile full color projectors and laser displays, plastic fiber communication, data storage, heads-up displays in automobiles, which are now you see them in a lot of automobiles, but they use other kinds of bulky lasers, and of course, solid-state lighting, medical applications, and so on. Now, in the nitride materials, there is a problem. In the C-axis, and most materials, most of the work is with C-plane nitrides, you have a very large polarization field, and there's spontaneous and piezoelectric polarization. And that means that the heterostructure band diagram looks something like this, and the electron hole wave functions are inherently separated. This results in large lifetimes and very poor quantum efficiencies. It also, as you inject, there is screening of this piezoelectric field, and that leads to a blue shift of the emission wavelength, which is also a bit of a problem. In addition to that, in quantum well devices, which are all used in the industry to make these blue lasers and other blue LEDs, as they add more indium, this leads to compositional non-uniformities. And in fact, what is seen is there is 0.6 to 0.7% decrease in efficiency for every nanometer of wavelength shift. And this leads to what is known as the green gap in the industry. So beyond green and beyond, with quantum wells, you just can't do it. And so two papers arrived. An early paper by Ian O'Reilly in Cork in Ireland, And he calculated the polarization field in quantum wells and nitride wells and dots and so on. And he showed that the polarization field is much smaller in quantum dots. And it's expected because these quantum dots grow by strain relaxation. And that's what he showed. And then Jaspreet Singh and his group here also actually calculated the overlap integrals and radiative lifetimes in these quantum dots and compared them with wells. And it's clear that the lifetimes in the quantum dots are at least 2 orders of magnitude smaller. And when I looked at these results, it was clear that this is the ideal. This is perhaps even a more important system than arsenides and phosphides to use quantum dots, because you have this additional advantage, all in addition to all the other things about quantum confinement and large gain and differential gain and all that. You have this additional advantage of a lower polarization field. And so, to make a long story short, we made the first quantum dot laser actually in the nitride system, which lased at the green wavelength, and then followed it. And you can see, we measured the polarization field, and you can see the blue shift with current density is much, much smaller than even semipolar quantum well lasers these were being made at Nakamura-san's company, Sora. Then we followed it. We went even further. Now, nobody had gone to red in the nitrides. So this was the first venture into red, and these are red lasers. You can get very decent amounts of power. This was all done by student Frost and Thomas Frost, and so we had a contract with Denso, Toyota Denso, to demonstrate these lasers, that they could give sufficient power, show temperature stability of the threshold current, and work at high temperatures. And we showed operation up to 95 degrees centigrade. And the thresholds we are getting was lower than what they had stipulated. So now they have taken it over, and they are developing this in Japan for heads-up displays. One other interesting application of these, now that we could make red quantum dots and all the other colors, green and blue and so on. Now, coming back to solid-state lighting, what we have now and what we call solid-state lighting is really not solid-state lighting. What we do is we excite yellow and red phosphors with a blue LED. And in such phosphor-converted LEDs, you have internal losses due to Stokes shift. You have backscattering of the pump and converted light by the converter, by the phosphor layer, and you have non-radiative internal losses. In addition, you have poor temperature stability and reliability, and actually all the money actually goes in developing and improving that phosphor. The blue LED is perfect. It has quantum efficiencies of approaching 90%. I would say almost 100%. But so what is really needed is an all semiconductor converter LED or an RGB. So with these, the red dot capability, and we were under contract with Osram from Germany, and we said, okay, so I think and they had tried this converter thing in their labs in Regensburg with quantum wells, and they got results, and I said, I think we'll get better results with quantum dots. So what we have is multiple layers of blue or active dots, and they excite passive multiple layers of red quantum dots. And what we get out is white light. And that's white light under the microscope, of course. But if you look, and that's the luminescence output from these LEDs, and you can clearly see the blue emission and the red. And the good thing is that you can now tune these things. You can, by varying the composition, the number of dots and all that, as we have done here, the pump dot emission wavelength and the converter dot, you can tune these things and go all over the map in the configuration, in the color, coordinated color diagrams. and you can vary the chromaticity coordinates and therefore the correlated color temperatures. And we can go all the way from warm to cool temperatures, and we didn't go further. And now, so they were very excited with these results, and we could go even below. We know we could go even below 4,000 to go to true warm colors. And so now they are following this up themselves at Regensburg. And you see the extreme stability also of these correlated color temperatures with pumping, and that is because of the low polarization field. So the last thing, now I'll switch to really the present, 2016 and 2017. We have been growing nanowires just like Zetian. Our nanowires with the nitride system are self-organized nanowires, arrays of nanowires. And we grew this Grinch structure, laser structure. And here's the active region and what is new here is we went all the way to indium nitride. And nobody had ventured to put indium nitride in these nanowires and so on. And so here's some collaboration with Joanna. And she showed that these nanowire regions, they are cylindrical dots with an indium-rich core surrounded by a slightly gallium-rich shell. But nonetheless, they were quantum dots that were forming. And that was also, and you see this blowout, and that was predicted by theory. It has to do with the atom kinetics on the growing surface. So we made lasers out of these, and lo and behold, these lasers actually laze at exactly 1.3 microns. And they show very good temperature stability again. And so one of my students here, Arnab, he actually then made a photonic integrated circuit of a laser, a passive dielectric waveguide, and a detector, a waveguide detector. And here you see that photonic integrated circuit made with the same nanowires. And so this is a photonic integrated circuit, something that may be used in silicon photonics, where the active source, the passive waveguide or modulator or whatever, and a detector, they're all there on 001 silicon platform. And here's the detector response or the photocurrent with injection current to the laser. So that's another, and the laser, by the way, is just like a bulk Fabry-Perot laser. It's an edge-emitting laser, and that's what you see. So with that, I think I'll stop with this view graph. So where are quantum dot lasers? When we first started working on these quantum dot lasers, and we would have reviews of our programs and so on, I remember one person, he made this comment that the only dot I want to see is at the end of a sentence. So it like everything else, there was a lot of doubts. Nobody believed in it, and so on. But we persevered, the three groups at least around the world. And now this is the status. 1.1 micron lasers are marketed by the millions for the second harmonically generated green lasers. The 1.3 micron lasers are universal. In all 1.3 micron communication, including the short distance, the passive optical network communications, they're all 1.3 micron quantum dot lasers. Gain chips and gain modules are again used for tunable diode lasers. The and this is the most recent thing, the 1.55 micron lasers, I gather, are going to replace all long-haul lasers as more systems come into use and are inserted. They're all going to be these quantum dot lasers. These red lasers that we made with the nitride systems, I'm hopeful that Denso will someday start putting them in the Toyota automobiles. And the amplifiers that I talked about, the wideband high-power polarization insensitive amplifiers. They are used for very high performance circuits. But also what the work from these three groups, including ours, what it did in the early days, it made other people realize that quantum dots with their high gain, with the high intensity and the narrow line widths and so on are good for as display materials. So you have all these other things that gradually emerged, like colloidal quantum dots, like 2-6 quantum dots, which are now used in displays, and you already have quantum dot TVs in the market, and so on. These are all offshoots of all this work that happened with the self-organized quantum dots. So as Yasu believes, and he says, in the near future, all semiconductor lasers will be quantum dot lasers. I hope that's true. So to acknowledge, of course, I must acknowledge all my collaborators here in Michigan, and I haven't listed the ones in other places, but there's Rachel Zetian, Joanna, Ted Norris, Brad Orr, Jamie Phillips, Jaspreet Singh, Duncan Steele, and of course generations of doctoral students, postdoctoral researchers, and other collaborators, and the funding has come from several DoD agencies, NSF, NASA, industry. You know, we don't pick and choose. We take whatever comes and wherever it comes from. That's who we are. Thank you.